afternoon. It's nice to see all of you here. Our speaker today is Bobby Farlise Rubio. He is a science and culture educator with more than 2 decades of experience working in Vermont's Northeast Kingdom. He is a regular contributor to the North Star monthly newspaper from Danville, where his column is entitled, Consider This. From 2023 to 2025, Bobby served as a state representative in the Vermont House for the District of Caledonia 1. Number 1, which encompasses the towns of Barnett, Reigate, and Waterford. For 3 summers, Bobby has worked as a park ranger at Stillwater, Big Deer, and Salem Lodge State Parks and Groton State Forest, as well as Elmore State Park. For 8 years, Mr. Farlise Rubio was regularly seen in his monthly Starstruck segments on Channel 3, WCAX-TV's 6:30 p.m. news, on which he presented the latest happenings in the field of astronomy. During his 18-year tenure at St. Johnsbury's Fairbanks Museum, Bobby was the teacher for the Guinness World Record largest astronomy lesson. Raised in Hialeah, Florida, from Cuban and African American roots, Bobby is also an avid musician who plays in the local band Tritium Well as his solo musical endeavor, Bobby and the Isotopes. Bobby is the father of 3 Vermonters, the oldest of whom is currently serving in the U.S. Air Force. Bobby currently resides in Barnett, Vermont. Now, some of you will remember that he spoke to us on Halloween 2 years ago on werewolves, vampires, and zombies.
I'm sorry.
Today's program is The Outer Limits, exploring the extremes of astronomy, and I know you will find it out of this world. Please welcome Bobby Farlise Rubio.
Mic's working, otherwise I can just be loud. Thank you, Marita. Thank you, Marita. Thank you, Karen, for a wonderful introduction. I will start with a little clip to kind of get your mood right, because if you remember my talk about vampires, this one's going to be even weirder.
There is nothing wrong with your television set. Do not attempt to adjust the picture. We are controlling transmission. If we wish to make it louder, we will bring up the volume. If we wish to make it softer, we will tune it to a whisper. We will control the horizontal. We will control the vertical. We can roll the image, make it flutter. We can change the focus to a soft blur, or sharpen it to crystal clarity. For the next hour, sit quietly and we will control all that you see and hear. We repeat, there is nothing wrong with your television set. You are about to participate in a great adventure. You are about to experience the awe and mystery which reaches from the inner mind to the outer limits.
I didn't exactly make that up, but I grew up watching old TV with my dad, so you can blame him for that. So let's begin by talking about what we know as the state of the science in astronomy. It's going to start with a very rapidly developing history of the universe. So, 13 billion years in a few seconds. No big deal. Here you go. The Big Bang, as we like to refer to it. Let's see if I can make it happen. There was light. And we quickly go from a Big Bang to the development of stars and galaxies and rushing forward to the present. And that is a very strange occurrence in and of itself, because how do we know that the Big Bang occurred? Well, everything we look at, we see it moving. And if we run the clock backwards, everything is going out. So if we go backwards in time, everything had to go in and everything comes from a common point, a point of infinite density and infinite gravity, something that basically our mathematics and our physics cannot explain because it doesn't fit with our understanding of how the universe works today. But we still find confirmation of this in everywhere we look. And trust me, I'll be shouting from the rooftops if we find anything that tells us otherwise. But so far, this is sort of that same video that you just watched, but in a simpler two-dimensional format that shows the beginning and then the oldest light that we can actually detect with our telescopes. It's microwave. It's a form of higher energy radio waves. And we have fancy telescopes that can show us that microwave background radiation, as it's called, or sometimes the CMB, cosmic microwave background. But believe it or not, we already knew about this before we had fancy telescopes that could see it. When you were kids, when I was a kid, all you had to do was turn on a radio or an old television and tune to a place where there was no channel. What did you see? Snow, right? Or you heard the shh of static. That is that. That hiss that you hear on the radio is the cosmic microwave background, the oldest light detectable in the universe, sort of the echo of the Big Bang. So it's not the Big Bang itself, but it's when all these little atoms started to fling together. Things got cold enough for protons and electrons to sort of become atoms, and that created a lot of radio, and that's what we picked up. You can imagine radio was invented over 100 years ago. People like Tesla and Marconi made the technology work, but you would have thought it would be silent, because until we invented radios, who was broadcasting? Well, the universe has been broadcasting since the very beginning. And so we can still pick that up today, although most of our TVs don't, are digital, and they don't have that fun feature of looking at the ancient light of the universe. So let me move on to a picture that you may have heard of, taken by the very famous Hubble Space Telescope, which has now been not replaced, but sort of succeeded by the James Webb Space Telescope, which is even 100 times better than this. But look at this image, and you might think I'm showing you stars, but I just want to point out that that is a star in our galaxy, in our neck of the woods, and there's another one there, and another one there, and you can tell they're stars because they have that plus sign look to them. And that's not the star doing that, that's the telescope. If you look at the Hubble Space Telescope's construction, it has a secondary mirror held in place by two brackets that are perpendicular. So those brackets cause a bit of an effect, a diffraction as it's called, if you want to get technical. And it's funny because this happened with the first telescopes before the Hubble, and you can tell in the history of art, if you look at paintings, people used to draw stars. Well, Van Gogh had his crazy spirals, but most people did stars as points or little star. And then when telescopes and photography got combined, all of a sudden all the artists of the world started making stars with plus signs as if that was more accurate. But that was actually an artifact of using telescopes. So with that out of the way, think of these things as being in the foreground, and the background are not stars, but other galaxies. This is just, they pointed the Hubble Space Telescope at a part of space where they thought it was kind of empty. In the constellation Fornax, they said, there's not much in that direction. There's only a few stars that we can see. Let's see what happens if we turn the shutter on and open it for 30 days. So you've just like a long exposure photography, 30 days of having the shutter open, all that light flooding in, and this so-called empty spot in our sky is filled with that many other galaxies. That's just to give you an idea of how much is going on out there. And we live in the Milky Way galaxy. Our galaxy has around 200 billion stars. Some of these galaxies have 1 trillion stars. And just to give you a starting point, the number of stars that we estimate are in the entire universe, all the galaxies put together, would be a number 1 with 24 zeros following it. 10 to the 24th power. That's how much there is in the universe as far as stars are concerned. And to add that to that we now estimate that most stars have planets, because we've already found about 6,000 of them. Then just think of that 10 to the 24th power is not even the complete number of planets that might exist in the universe. So I'm not going to go into about whether or not life exists outside of the Earth, but you start to see that even if it was 1 in a million or 1 in a billion, there would still be tens of billions of places with life. So that's something to think about. And that's not even the best picture we have, because the same picture but zoomed into a small section of it, and they found even more galaxies. Spiral galaxies, elliptical galaxies, barred spirals. They have all these different names. Think of them as like animals at the zoo. All of them are telling you how they formed or how old they are, how big they are, but there's just so many of them. And to give you an idea of how much of the sky this represents, the first picture I showed you is this big compared to the size of the full moon. The second picture I just showed you is only that big, the extreme deep field. So in that tiny little window, like holding a pinched fingers into the sky, that's how many galaxies you would see in that direction. And that's just one direction. It's the same in every other direction too. So that's how much universe we have. And then we have to talk about the fact that that picture is not a static shot in time. When you think of a horse race and the snapshot, you know, the photo finish, you're thinking of a picture as showing you one moment in time. But when you take pictures with a telescope like this, you're looking at several billion years of time. That's because the farther away stuff is also longer ago. I know this is weird, but that's why we're here. This is the fun of this. So the stuff in the background, we're seeing what it looked like 9 billion years ago. So an astronomer would tell you it's 9 billion light years away. You want to see what it looks like right now? Sit tight and wait 9 billion years, because what those galaxies are doing right now is not going to reach our cameras and our eyes for another 9 billion years. And just for reference, the Earth is estimated to be 4.5 billion years old. So we're looking at stuff that's older than our own planet. And the news is just arriving now, because light takes a while. Even though light is the fastest thing in the universe, it still takes time to travel to us. And the speed of light, in case you haven't memorized this like I have, is 186,000 miles per second. 671 million miles an hour. If you could travel as fast as light, you could circle the Earth 7 times in 1 second. You wouldn't see much, but that'd be fun. And if you could travel as fast as that, circle the Earth 7 times in a single second, it would still take you billions of years to reach these things that we're photographing with our telescopes. So, just to show you a little bit of an upgrade, this is a cool little animation of the James Webb Space Telescope that's been in space for quite a while. It's more than 1 million miles away. It's not in orbit around the Earth. It's actually orbiting the sun in a strange place called a Lagrange point. I'm not going to go into all the mathematics, but it allows it to be far enough from the Earth and the sun to get a good view without the heat of the sun affecting its camera, because it's an infrared telescope. It actually sees the light that we don't see with our eyes, the light that we feel with our hands. You know, pick up a warm puppy or put your palm of your hand an inch away from your forehead and you feel the heat coming off of your body. That's infrared light. Your eyes don't see it, but your nerves detect it. This thing is a heat detecting telescope, basically. And because of that, it has to have a gigantic mylar screen, a shield to protect the sunlight from shining on it, because we want that telescope to be cold as possible so that it can detect heat more accurately. And the sunny side of that shield, which is the bottom on this, will be around room temperature because the sunlight is constantly shining on it. But the far side of it, this side would actually be pitch black if it were really in space. And this side of it is about 400 below zero. And then they have a refrigerating unit on the back that cools it down even more. I got to see this thing being built at the Goddard Space Flight Center in Maryland. With my own eyes, I got to walk up to a room, into a glass window, and look down into the world's largest clean room, where all the folks were wearing hairnets and, you know, those Tyvek-looking suits, and they were putting it together. So I got to see this being built before it launched. So that's the successor to the Hubble Space Telescope and our best eye in the sky. Just to compare the sizes of the mirrors, the Hubble's mirror is this big, and the JWST's mirror is that big. So it's like having a bigger eyeball. The better to see you with. So let's just do a quick comparison. This is the famous Ring Nebula, something that you can see in the Summer Triangle, still visible tonight. If you're an astronomer, you've probably heard of Lyra, the constellation. And if you use a telescope, you can see what looks like a Cheerio floating in space to a backyard astronomer. And to the Hubble Space Telescope, it looks like this. And with the James Webb Space Telescope, the same object looks like this. So that's just to give you an idea of the detail that we get. It's less blurry, it's sharper, and we see a lot more features that were otherwise invisible. Plus, we're seeing not just the light, but the heat. So we're knowing where it's warm and cold in this image, as well as bright and dark. So there is the Hubble Extreme Deep Field, and then here's the same part of space with the Webb telescope. Well, in this picture, you can't quite see the difference, but everything is a lot sharper. So we have this wonderful eye in the sky, but it's not the only thing that we use to understand the nature of the universe. We have other forms of light that we can see. I already mentioned infrared, but we're going to talk about some of the other wavelengths. So this is what you started with at the beginning, now with labels. And I'll just quickly point out a couple of things. Quantum fluctuations is what we call the Big Bang. Inflation, and then the afterglow light pattern. That's what I told you was the cosmic microwave background. Then we have a strange period for about 400 million years where the universe was just dark. There was matter, but it was all getting spread out, cold, cooling down, and not making enough light to detect. So we call it the Dark Ages. And then gravity starts to take over. After being flung out by a lot of energy from the Big Bang, things start to clump together, a little bit at a time. One atom of hydrogen and another clump together, and then all of a sudden they have more mass, they have gravity, they start attracting the ones nearby, and like a snowball rolling downhill from a little clump of gas, you can start to get the formation of a nebula, and then the fusion at the core that begins the stars' lives. And so the first stars happened about 400 million years after the explosion of the Big Bang. And then we get stars clumping together with gravity into the structures that we know as galaxies. And then here, see how it looks like a bugle, how it's starting to flare out? This is one of the weirder things in astronomy that when I was a kid, I mean, it was only when I was in high school that they used to tell us the Big Bang gave the initial push and maybe gravity will eventually take over and the universe will be crunched back down. And so it kind of gave the idea that the universe might have expanded and then it would contract and then maybe it would all start over again. They called it the Big Crunch, to contrast with the Big Bang. Well, that is no longer thought to be the case because since the 1990s till now, we've discovered something that they call dark energy. And it's basically something like the opposite of gravity. A new force that appeared sometime a few billion years ago that is now causing the galaxies to spread apart faster than they were before. So it's a new form of energy. Dark implies it has bad motives, but that's not what it means. Dark is the term when we don't know what it is. So we have dark matter, which I'll talk about, and dark energy. But combined, dark matter and dark energy constitute about 95% of the universe. And the stuff that we see, the twinkle, twinkle, little star, all the galaxies, all that stuff I showed you, all of the stuff you see here is only about 5% of what's there. So right now, we are at a point where we realize we've come a long way. We've discovered a lot, only to discover that we only know about 5% of what's there. And that's a good place to be because there's 95% of the universe left to be discovered. It's dark energy, which causes things to expand, kind of like the opposite of gravity. Gravity, maybe getting a little silly here, but I always think of gravity as like love. It's unconditional. It accepts everything, no matter what you are, no matter who you are. Gravity will accept you and pull you in. Dark energy is like the opposite. It doesn't matter what you are, it'll push you away. And so we have dark energy and gravity as two competing forces, and then we have dark matter, which has gravity, but we can't see it. So it's like gravity without an obvious source. I can say the Earth has gravity, and I can see there's a land here that's pulling me into it. But dark matter is like gravity without an obvious source. So it's made out of something that we just don't know how to see yet. Okay, so here's another version of that same image. Just to, put it into perspective, we live here, and we can still see here because the light from back then, that far away, is still arriving. And just a word on light, because I want to make sure we are all speaking the same language here. I hear a lot of people talk about radiation, and they get freaked out about things like power lines and cell phones. My cell phone is on Wi-Fi right now, and that means it's broadcasting and receiving in the microwave. So I think it's funny how some people are afraid of microwave ovens, but they'll have a Wi-Fi router in their house. the microwave oven has the microwaves contained in a box. They can't leak out. But the Wi-Fi router is designed to spread the microwaves all over your house. So, you know, I think people get a little bit of fear. All light is called electromagnetic radiation. I'm not talking about alpha radiation from a piece of uranium. That's a different kind of particle radiation. But light comes in all these flavors. Radio waves, which we can see with telescopes, but we use it for broadcasting too. Microwaves for cooking or for Wi-Fi. Infrared, we talked about it, that's heat. That's what you feel coming out of warm things. Like when I walk into my kitchen or my living room where there's a wood stove, even if it's pitch black, I know where the wood stove is. I can feel the infrared light coming off of it. It tells me where it is. Visible, that's the rainbow. That's the light we see with our eyes. Ultraviolet, that's what gives you a sunburn at the beach, but it's also something that we can detect in outer space. UV light. X-rays at the doctor's office, you know, the dentist, and then gamma rays, which you will only experience if you are foolish enough to step into a nuclear reactor or witnessing an atomic bomb, which means you have other problems to worry about. So just to give you a visual, NASA made a really nice video with the city of Seattle. So you could see radio waves. If you could see radio, then every antenna, like the Space Needle, and every antenna on every building would be pulsing light. But you can't see radio, so you never notice this. If you could see microwaves, you would see every Wi-Fi router and cell tower in a city. They would be like bright lights, but we don't see microwaves, so you don't notice this. And by the way, those waves are about the size of a bee. Well, we won't get into that. But infrared, heat. Every building, everything that's not absolute zero at cold temperatures is giving off some light. So even a dead object is glowing in infrared. Optical, well, that's what you expect to see because that's what we see with our eyes. Our eyes evolved to see optical light. Some creatures can see infrared, some creatures can see UV, like deer. I'm not a deer, but if you could see ultraviolet light, even at night, a city would not be dark. And ultraviolet light, you can see, is coming from outer space too, but we just don't see it with our eyes. And then X-rays, well, guess somebody's getting their molars photographed at the dentist's office scattered around Seattle. Otherwise, you're not going to see X-rays coming out of most human environments, but they do come out of space, as you can see in the background. And then gamma rays. Only the most energetic and deadly things can make gamma rays. Let's keep Seattle dark in that regard, please. But you can see that outer space is a source of gamma rays. The good news is that those gamma rays are dangerous, but they don't penetrate our atmosphere. Our atmosphere is opaque to them. So if we want to see gamma rays in space, we have to put the telescope outside of the atmosphere in space, and we have telescopes that can do that. So that was a crash course in the nature of light. Let's put it to some practical use to understand a beautiful galaxy that is called the Spiral Galaxy M51, well known to backyard astronomers near the Big Dipper in the night sky. This is how it looks to the Hubble Space Telescope with its great optical resolution. And then we're going to switch it to infrared heat, which we have one telescope besides the James Webb. We also have the Spitzer Space Telescope that can see infrared. So you can see that's a very different looking picture, but it still matches the structure. And then X-ray. Whoa. Everything that's bright in this is giving off X-rays, and that's usually caused by exploding stars like supernovas or colliding stars. A kilonova, which is a new term for when two neutron stars collide. And here we put them all together. So I would like to say that modern astronomy is this. It's all the flavors of light, whether you see it or not, combined together, and this is what gives us the picture that we have of the universe today. So I hope that makes sense. We're going to move on. So now you have a contrast. This is the new Webb telescope and the older Hubble Space Telescope. The Webb is more looking at infrared, but that heat tells us where new stars are forming, where there's a lot of activity and where there's less. So you can see that combining those two, that's why the Hubble hasn't been replaced. It still has a use, and it informs what we see with the other telescopes. So, oh, I guess I have that slide in there twice. So, just moving on, let's talk a little bit about the microwave, the stuff that we talked about that's back here, the oldest light that we can detect. Well, here's a little progression of our improvement in technology. Kobe was the first microwave satellite, and this is how blurry its vision was. And you can see as we got to the Wilkinson Microwave Anisotropy Probe, the WMAP for short, And then the European Space Agency has the Planck telescope, which you can see is just a better picture. It's just more resolution, less blurry. And that is what gives us a hint as to what happened at the very beginning of the universe. But here is the entire universe as seen in microwaves. And you're going back in time, so in places like that is where things evolved, where stars started to form, galaxies started. This is like watching 1 billion years of time fast forward. It's pretty cool. So the microwave background is like seeing the starting point before everything started to form, before the stars even existed. What was the universe doing? And it was not even. This is one of the weirdest things that we've discovered, is that if you had to guess, when the Big Bang happened, you would have thought that everything would have been evenly heated. Everything would have been the same temperature as it expanded. But even at the very beginning, there were cold spots and hot spots. And the cold is the blue and the hot is the red. So you can see that it is uneven in temperature. And that actually set up the stage for the formation of the stars and the galaxies. It might not surprise you that more stuff happens where it's hotter than where it's colder. So the early state of the universe predicted what we see now happening. And so this is pretty cool. This is like, I don't know, this is like looking at a person and seeing the sperm and the egg that met before they became a human being, you know? This is kind of what we get with the universe. So, and then I have to add in another feature that allows us to see sometimes even farther than we should be able to see. We sometimes can use gravity as a tool to help us bend light and magnify it in ways that would not otherwise be possible. And I'm putting up this very famous picture. It's not important that you remember it. It's called Abell 68, the galaxy cluster. But I just want to see if any of you observant folks notice that in this picture there appears to be something looking back at us. Do you see it up there? What is that? I belong to a generation that was trained to defend our world against those kinds of things. Let me zoom in on it. That looks kind of spooky, doesn't it? In fact, it reminds me of exactly what I used to go. I used to go to this combat training center called a video game arcade. That's right. I was trained how to fight these things off from destroying Earth in a game called Space Invaders. See, we're all safe, folks. We're all safe. The video games of today are nothing like this. The kids will never know these simple joys. But, okay, enough joking around. What's really going on in this picture? So, what you're seeing is one of the coolest and funniest examples of gravitational lensing. Gravity bends light. Light is really fast, but when light is traveling in a straight line near something that's very massive, it will affect the path of the light and bend it. Just like a lens, just like a magnifying glass, or a funhouse mirror. Think of how fun that is when you go to one of those bent mirrors and it makes your head look huge and your feet look tiny or all that. Space does that to us too. And I put a fake magnifying glass in here just so you understand. This is a bright galaxy that's in the foreground. It has a lot of gravity. It is massive. It's bigger than our galaxy. So there's trillions of stars worth of gravity in there. And here is another galaxy that actually looks quite normal and unthreatening. It's a spiral galaxy with a yellow core, and that one is in the farther background. So because of the gravity of this object is actually diverting some of the light that would go to the telescope in a straight line, it's getting bent and split and mirror imaged. So can you see how this is the source of this? This is an optical illusion. But imagine if you didn't know that. You'd be getting ready for an alien invasion. So gravitational lensing, it was actually something that was predicted by Einstein in his theory of relativity. But in his lifetime, we just didn't have telescopes quite sensitive enough to be able to pick that up. And now we can see what he predicted 100 years ago. So more of that. You go back to the original image. And if you look at this, you can see there's a lot of other things that are smeared or distorted. And right here, that little streak is actually another galaxy that its light is getting stretched out, so it looks like in a funhouse mirror way, a distorted version of what it really is supposed to look like. So gravity bends light, and we have to factor that in when we're looking at things in space with telescopes, because the gravity could be distorting what we see, but just like a magnifying glass, gravity can also amplify what we're seeing by concentrating and magnifying the light, allowing us to see farther away than we would have been able to see without that effect. So, something I could talk all day just about this alone, but I got to move on. So, this is the Webb Space Telescope. Remember I told you about the plus signs that the Hubble Space Telescope made the stars appear? Well, guess what? Webb is not based on a perpendicular bars holding the secondary mirror. It's actually made out of hexagons. So can you see what effect that has on the pictures we take with it? Instead of a plus sign, we get an asterisk now. And that's because of the structure of the Webb telescope. So don't be fooled. That's not the star looking like that. That's an effect of the telescope's construction. It's an artifact. But we know that it also helps us identify what's closer and brighter. And then the more distant objects that are more diffuse don't have that. So you can see these galaxies. But do you see the lensing here? So here is the lens source, the gravitational source, that's causing everything behind it to look distorted. And you can see that it almost is perfectly circular in the orientation because it's all being bent by the thing in the middle of the picture. So even the Webb telescope can see that gravitational lensing, but being 100 times better than the Hubble, it just makes it sharper and clearer and easier to see. Okay, so here's the fun part now. Let's talk about the stuff you can't see in that picture. A lot of that distortion isn't just caused by the bright galaxy, but by the cloud of dark matter that surrounds it. And dark matter is very hard to explain, but I've had my best luck explaining it by using a metaphor that's very appropriate in the fall. Think about going to an apple orchard to pick some apples. Now imagine that the apples look like that, stars and galaxies. And imagine that for most of history, we thought that those apples just appeared in space. Oh, here's an apple, randomly distributed in the orchard. And for centuries, we had no idea that there was such a thing as a tree holding them together. So if you could only see the apples, imagine what an orchard would look like. Little orbs floating in an empty space. And then, not knowing that between two apples is a big wooden branch, you go take a big stride and walk right between them and clonk your head on something you can't see. So imagine the tree is dark matter and the fruit is visible matter. And that's, to me, the perfect analogy for what we've discovered. But it took a while. It took astronomers like Vera Rubin, who now has a giant observatory named after her in Hawaii, and Fritz Zwicky, a Swiss astronomer who had the best name in the business. Fritz Zwicky, come on. So Fritz Zwicky and Vera Rubin both made separate but parallel discoveries of what we now call dark matter. Vera Rubin worked at the American Museum of Natural History in New York City, and Fritz Zwicky lived in Europe. But now let me put some wood to the orchard. Let me put the tree branches in. This next image I'm going to show you is a computer simulation based on where we think all the dark matter would be if we could see it, and it adds in the stars and galaxies that we do see, like the fruit on the tree branches. This is called the Bolshoi simulation, and this is what the universe would look like if we could see the dark matter. It does look like a tree, doesn't it? This is not the whole universe. This is just a small section with that many galaxies. You already know how many galaxies there should be, so there would be no way to draw that. So notice how there's a bunch of separate galaxies, but they're all kind of connected on a branch. The branch is the dark matter. So things aren't so random anymore. Remember that picture of the microwave background? It wasn't random. It was sort of hot, cold, different concentrations. Same thing we find with dark matter. There are places where there's a lot of dark matter, and then there's places where there's almost none. This is like the gap between two branches on a tree. You're going to find lots of fruit on a branch. You're not going to find any fruit where there's no branches. So, now that you kind of understand that, I hope, well, there's more dark matter. There's 5 times more dark matter than there is visible matter. Just like how there's more tree than there are apples, right? If you weighed the apples and you weighed the tree would probably be a lot heavier. It's the same thing with the universe. And let me just show you a little animation. This is like fast forwarding through time as the Big Bang happened in the microwave background, the heterogeneous distribution of matter. Then you had the coalescing of dark matter into these tendrils that are like branches. And that's where all the galaxies and stars form. That's where all the action happens. So what happens in the voids? What's going on in the places where there are no stars forming? The space between the branches is dark energy. That is the place where, instead of gravity working the way it does, unconditional love, accepting everything, dark energy is pushing things apart. And what we have discovered is in the last couple billion years, those voids are expanding. So basically, space is getting bigger because the empty spots are ballooning out. And it doesn't necessarily mean that we're in danger. It just means that our little neighborhood of apples, our galaxy neighborhood, is getting farther away from the next galaxy neighborhood. And if this acceleration that's caused by dark energy continues to happen, there might be a time when we won't be able to see those things, because the acceleration of dark energy is actually capable of expanding faster than the speed of light. So it's a kind of a sad fact that several billion years from now, a lot of those things I showed you in those pictures won't be visible anymore from Earth, because they'll be accelerating farther and farther and farther and farther away, faster than light can catch up with it. So there could be a time in the far, far distant future, if humanity is still around, where they say, our ancestors used to talk about these things called galaxies, but I don't believe they exist because I haven't seen them myself. Maybe they were just made up legends like dragons and fairies. I don't know. Could you imagine humanity doubting the stuff that we take for granted today? I don't know, but it's something to consider. So this is why some people would say we're in a very special time, because we have the intelligence and the technology to see this stuff before it's too late. And so a lot of discoveries happening right now are sort of in a sweet spot. So to summarize everything that I've just talked about, here's a simple pie chart. The universe is 68% or so dark energy, the expanding stuff that sounds like the nothing from the never-ending story. Remember that? Dark matter, which is invisible but is still operating under the attractive force of gravity, the branches of the trees. And then the apples, the stars, the galaxies, you and I, the planet Earth, is only 5% of the whole universe. That could end it right there, right? You know, like that's all that we know. We now know how little we know, which is a good place to be if you want to discover things. Okay, let's talk about size now. The moon, Mercury, about a third the size of the Earth. We're going to bring it back a little bit less abstract. Mars, about half the size of the Earth. Venus, if it didn't have an atmosphere, is almost exactly the same size as the Earth, and I hope you recognize this next one. Spinning the backwards, but it doesn't matter. Neptune is about the same size as Uranus, but nobody wanted to see Uranus, I guess. And Saturn, without its rings, is the second biggest planet in the solar system. And there's Jupiter, 1,300 times bigger than the Earth. But the sun is 1,000,000 times bigger than the Earth. And the sun is pretty small compared to other stars. Sirius, the bright star that you'll see next to Orion at the night sky, is big, but not as big as Pollux in the Gemini constellation. And then we have Arcturus in Boötes, one of the brightest stars of the summer sky. Aldebaran in Taurus the bull, even bigger. This one, Rigel, that's Orion's left knee, visible tonight. And then this one, you got to go to the southern hemisphere to see, the Pistol Star. And then Antares, the heart of the Scorpion constellation that you saw all summer long. Mu Cephei and Cepheus the King, visible tonight. Look how small the sun looks over there. You can't even see it anymore. VY Canis Majoris in the Big Dog constellation, like Sirius, is the largest, one of the largest known stars. We have a couple others that are even bigger. And let's go back to the size of the Earth for comparison. Okay, so you see why astronomy is fun? You have to have a very nimble imagination to fit this stuff in there. It stretches, literally, it stretches what you can imagine. And so, yes, there are stars that big. The sun is small, but let's be glad for a moment, because small stars last a long time. The sun has been around for about 5 billion years. Big stars like this, well, they're like rock stars. They live fast, and they die young. Stars like that size, like VY Canis Majoris, they only last for hundreds of millions of years. That's still a long time, okay? But what it means is that it doesn't last long enough for it to get a collection of planets that might evolve life, because as soon as any of that starts happening, the star is going to blow up. So the big stars are unstable. The smaller they are, the longer they last. So look at that. If you're petite, use that for, be encouraged. So you see, a supernova, you may have heard of it before. It is the cataclysmic destruction of a star. And a supernova is an explosion, but at the end of it, it yields one of two things. The core of the star will become a black hole, which was theoretical only on paper until a few years ago. Now we know how to take pictures of them. And a neutron star, which are easier to see because they give off light, but they're so dense. Well, I'll go into it more just to remind you, but to get it started in your mind. A neutron star, they all tend to be around the same size, about 12 miles wide, which happens to be the distance between Burlington and the Adirondacks, going across Lake Champlain. So imagine a star that could fit there in the Champlain Basin, but it would have more mass than the sun, 1.5 times the mass of the sun. So obviously we couldn't put it there because we'd destroy the Earth by doing that. But if I had a basketball-sized chunk of a neutron star core, think of a basketball-sized piece of material that weighs as much as the entire planet that we're standing on. That's dense. And that's what happens when big stars like this explode. Their cores get crushed into unimaginably small packages. But here is going back in time. This is before the Renaissance and before people figured out how to do foreshortening and perspective in paintings. This is a medieval king from what is now Germany, King Heinrich III. Well, Germany did not exist as a country yet. It was many small kingdoms. And he was on a trip to Italy, to Tivoli, and he saw a second sun appear in the sky, 1054 AD. It turned out it was actually the 4th of July. What a coincidence. Before anybody thought of fireworks and the Independence Day we celebrate on 4th of July, there were fireworks in the sky over the medieval world. And people saw it all over the world. This is the most obvious painting of this starburst. But the folks who lived in this country, in New Mexico, the Anasazi people, this is Chaco Canyon, one of our national parks. This was a bustling city around that time, 1,000 years ago. And somebody in one of the, this is a kiva, which would have been like an outdoor marketplace with a roof. It would have been like a mall in their time. And here's some houses. Out there in the background, somebody decided to paint a petroglyph of a starburst and the crescent moon and a handprint. Now, there was a crescent moon on the 4th of July, 1054 AD. And the crescent moon was near to where the starburst occurred. So that might be telling us that they were painting the same thing that the German artist painted on the other side of the world. And the handprint, according to anthropologists that study the Anasazi people, that is a symbol of something divine. Whenever they painted a hand, it meant something very important, holy, or sacred was occurring. So that, you see how similar it is to that starburst there. We may never know for sure, but these are probably referring to the same event. And in China, they didn't paint it, but court scribes for the Chinese emperor at the time wrote about a guest star appearing in the sky, like a new neighbor that decided to peek into the earth, and then it slowly faded away, like if it was a visitor. But what they really saw was this, a supernova, which is what would happen if you were in a starship watching a star that suddenly went boom, became 100 million times brighter than it was before. And then as it fades, you see that it's still exploding. All of this is the gas that was surrounding the core, and the center of it will become one of those neutron stars, or if the star was even bigger to begin with, it'll get crushed to an even smaller package, which we'll call a black hole. And when we look at that exact same star, this is the one that they saw blow up 1,000 years ago in 1054 AD. It's now called the Crab Nebula. So if you have a backyard telescope, you may have already looked at this before. It's one of the popular targets. And notice that there's a swirling whirlpool in the center. And do you see how this is a time lapse made by a gentleman named Detlef Hartmann, an amateur astronomer that took a picture of the same thing every year? And can you see how the cloud is still expanding? The explosion, this is 1,000 years post the explosion, but it's still exploding in a way. And the core that became a neutron star is spinning about 24 times a second. So the leftover core is spinning so fast that it's causing ripples and whirlpools through the gas that it's swirling in. And that's with a backyard telescope, but we have better pictures. The one on the left is an X-ray picture. You can see the spinning neutron star very clearly as a bright dot. The one on the right that looks red is optical. We can't see the neutron star because there's too much smoke and dust in the way. This is like a firefighter walking into a burning building and seeing nothing but smoke, but then they put on special goggles and they can see where the people are lying under the tables and chairs and find them because they have the right wavelength of light. In this case, X-ray cuts through the smoke and the dust, and we can see the neutron star clearly. Here's a static image from the Chandra X-ray Observatory, which is our X-ray telescope that's operated by Harvard. And that is the leftover piece of that thing that exploded in 1054. Now, I should tell you, this actually happened 7,000 years before 1054 because this is 7,000 light years away. So what we saw at 1054 was actually already 7,000 years before. Well, relatively speaking, yes. You must be an astronomer if you think 7,000 light years is close. Yes. So here is the neutron star, and you notice it looks like a foxtail coming out of it. There's another tail going in the opposite direction. It turns out that these neutron stars and even black holes have these jets of matter, relativistic jets, referring to the relativity theory of Einstein. They're things that are launching away from it. We're not exactly sure, but it might have something to do with magnetic fields. Think of how the Earth has a magnetic north and a magnetic south. These spinning objects might have really powerful magnetic fields, causing some matter to be ejected in opposite directions, north and south. So we're looking at, let's call this one south, and the north one is pointing away from us. We see that now, and we've actually used that to find black holes that are invisible because we can see the tails on either end. So I told you about this earlier, but this is the size of what that neutron star would look like. Next to the city of San Francisco happens to be where I was born. I didn't make this graphic, though. And it's spinning, so that's what's creating those tails that you saw in the image. And we still are not completely sure what they're made out of, but we call them neutron stars because the majority of their mass is neutrons. And just a little bit of a side detour into chemistry. You know about neutrons. You probably read about them or learned about them. Protons, electrons, and neutrons. Well, neutrons have no charge. Why? Because they were created by supernovas, and an electron and a proton got smashed together so hard that they became incorporated into one object that loses electrical charge. So every neutron in every atom is a little bit of this kind of stuff, which means, if you didn't already know it, we're made out of the debris from supernovas. Our entire planet is the dust, as a dust bunny of the dust made from these explosions. So every atom, almost every atom has neutrons. So just give you an idea of how much this is not separate from us. We are made of this stuff. And the reason why neutron stars are so dense is because the majority of the material has no electrical charge. Again, another imaginary, exercise here. You know the Notre Dame Cathedral in Paris? Okay, if we could make an atom the size of the Notre Dame Cathedral, then the electron's path would be running around those flying buttresses on the outer walls. And the proton would be on the altar right in the center of the cathedral, about the size of a basketball. And the space between that proton and the electron circuit going around the outside is empty in an atom. So every atom that you're made out of is mostly empty space too. Kind of like that dark matter, dark energy thing. You see a weird pattern there. And if you could take the electron and the proton and shove them together, then you would eliminate most of the volume that the atom takes up. And if you have something made out of mostly neutrons, you can pack them really together tightly, and there's very little empty space. It's like taking a piece of styrofoam and crushing it so all the air is missing, and then you get like a tiny little sliver of plastic. That's what a neutron is, and that's what a neutron star is. So if that makes sense, I feel like I've done my job, because that's one of the hardest things to explain. And then on top of the fact that neutron stars exist, we now know that occasionally two neutron stars will collide. So consider this a very fatal pas de deux in a ballet. The neutron stars are swirling around, gravity's pulling them together, and eventually they will collide. And what happens when they collide? Well, it causes a big explosion that we can see from far away. But it also creates gravitational waves. which is one of the newest things we've discovered. By the way, this is a depiction of a real kilonova, the collision of two neutron stars that happened a few years ago in the constellation Hydra. We saw it with visible light, we saw it with X-ray light, but then 2 seconds before the light arrived at our telescopes, we detected the gravitational wave of that collision, which means that now astronomy has a sixth sense. We can detect when big things collide because they shake the entire universe. Kind of like if you were blindfolded on a trampoline and an elephant got on the other end of the trampoline. You wouldn't need your eyes to know that something happened. And you would feel the entire trampoline move. Well, how do we feel a gravitational wave? Well, I'll explain that in a second, but let me just show you some more of the raw data here. So, a kilonova visible in the X-ray, visible in the optical. So, at that time, NASA and the European Space Agency and the Japanese Space Agency, JAXA, were just putting online what we call gravitational wave observatories. And I'll explain what that is in a moment here. But gamma ray telescopes like the Fermi and Integral, they also saw it too, that spike right there. This is the light, but this is the gravitational wave. And I want you to notice that it was detected 2 seconds before the light. So once these little graphs finish populating, you'll see what I mean. Light reached us, but the gravitational wave reached us 2 seconds earlier. Why? It's not going faster than light. It's just that this light had to fight its way through a bunch of smoke and debris. It had to get filtered by the stuff happening around the neutron stars, whereas a gravitational wave has nothing to slow it down. It's unimpeded, so it is actually getting here a little bit faster than the light that we can see. And what is a gravitational wave observatory? Well, I have a picture of one that we have in Hanford, Washington. There's another one in Livingston, Louisiana, and there are other ones around the world. Basically, there's a big building in the middle here and a hallway that's 3 kilometers, more than a mile long, and another one. And in this building, they take a laser beam and they shoot it through a splitter that splits the beam into 2 equal portions. One beam goes down one hallway, the other beam goes down the other. At the end of the 2 hallways, they hit a mirror, and then the beams come back into a camera. Now, normally, when the universe is quiet, these beams, they're running a race, but they started off at the same starting line. They're in sync with each other. Light acts like a wave, and as long as the waves are traveling the same distance, they'll be in synchrony with each other. They hit the mirrors, they come back to the cameras, they're still synced up. The only thing that will make them go out of sync is if one of the hallways is temporarily longer than the other, which means that when a gravitational wave passes through, the entire Earth is distorted. One hallway will be a few centimeters longer than the other because the entire Earth is wobbling like a jello mold. And that's what gravitational waves do. So now that we know how to detect them, we have a new power. And we have gravitational wave observatories scattered around the world. You can see that India has got one under construction. We've got the 2 in the United States. We've got 2 in Europe and 1 in Japan. And that allows us to triangulate from which direction the gravitational wave is coming. It's like having 2 eyes that allows you to see depth perception. We can tell the motion of the gravitational wave based on which observatory it hits first. So that means all around the world, the whole planet is kind of like wobbling, like a piece of wet dough. So if you know Einstein's theories of relativity, this wouldn't surprise you. We often use this kind of diagram to explain gravity. And so imagine if 2 of these things collide, that whole grid will shake. And remember how I showed you gravitational lensing, how light gets distorted by gravity? This helps you understand why. Because if you were traveling like a photon of light, a ray of light, and you were passing by something massive, what was a straight line is going to be a curved line as you go near the gravitational object. So hopefully this invisible force of gravity, illustrated this way, helps you understand both the gravitational waves, which would be like me shaking the grid, and just the normal distortions caused by gravitational lensing. So, we're almost at an hour. You folks are still with me. That's good. So, yes, it doesn't have to be a collision. We've also discovered gravitational waves with 2 black holes orbit around each other. And if I'm going to explain what a black hole is, I got to move along real quick here. So I promise. There, see the jet? See how that black hole is black? Because light cannot escape it. But it doesn't mean that there's nothing there that can tell us where it is. It has those foxtails, the relativistic jets, like the neutron star does. And it has the accretion disk, which is like the stuff that's swirling on its way down the toilet before it disappears. You can see it until it goes into wherever your septic tank, which is like the black hole. You're never going to see it again, I hope. So, you might. So, back to the kilonova, just with a little animation and a little sound. But this collision that we discovered, it didn't look like this. This is an animation of it. The gravitational waves and the light, you see how the gravitational waves took off first. It also created enough gold to make an entire sphere the size of the Earth out of gold. So yes, now you know where gold comes from. And that means that when you have gold in a jewelry or a ring, you have a little piece of that. So here is a black hole that is not an animation. This is actually seen with radio telescopes. April 2019. It took a network of telescopes connected together all around the world, the Event Horizon Telescope, to make this possible. And just about 5 years before that image, we had a movie that you may have watched called Interstellar with Matthew McConaughey in it. And in it, they have a black hole that won a science award because the artists that designed the black hole for the movie were the closest to the real thing when we actually started getting images of black holes. So they got an award for predicting what it would look like. And here's the real thing, again. And just real quick to show you where that is, in the Virgo galaxy cluster, another very densely populated part of our universe, in that big galaxy in the middle, over 100 years ago, we discovered that that galaxy has a strange tail. Sound familiar? M87 has a tail coming out of it. That was discovered 100 years ago, but it took us a while to figure out where that tail was coming from, and it's coming from that black hole. So, and just to show you how that image was made, they took radio telescopes all around the world and linked them together to make one giant eye the size of our planet. And that's how we were able to see that black hole. So here's the actual telescopes that took the picture, scattered in Hawaii, France, Spain, Greenland, Arizona, the South Pole, and Chile. They gave us an eyeball the size of the Earth. So, I'm coming around to the end, almost at home plate here. So, this is an animation of what you would see if you were that close to a black hole. Now, why does it look like a Mexican sombrero? Because that's actually a flat disk, but we can see the other side of it because the gravity of the black hole is so strong that it bends the light around so you can see what's on the opposite side of it. Just like the gravitational lensing that created that little Space Invader guy. The black hole is bending its own light. And if you fall into the event horizon, you're never coming out because the escape velocity of a black hole is greater than the speed of light. So if you go in, you're never coming out, like those Roach motels that they used to advertise, right? Well, so if we sent a probe, let's say we put a really cool satellite probe with all the antennas and all the bells and whistles we could imagine, and we sent it in there, we would never find out what it saw because the radio signals telling us what it saw would not make it out. Gravity would pull them down. So if you think about gravity pulling on light, you saw the gravitational lensing, you saw the distortions. It makes sense that a black hole is so dense that light cannot even get out. It gets swallowed up by it. But if you're on the accretion disk, you haven't quite fallen past that event horizon, that threshold. You're still visible because light can actually escape that part. And so if you're in that part, you're certainly doomed, but at least we'll see you. You're not going to get out of that easy anyway. But, so this is all of the labels to give you an explanation of what's going on. Kind of cool that the Doppler effect explains why this stuff is brighter because it's moving towards us. And that stuff is dimmer because it's moving away from us, similar to how the train whistle sounds high-pitched when it's going towards you and low-pitched when it's going away from you. The same phenomenon. It affects light just as much as it affects sound, the Doppler effect. But this is something that are very numerous. They were theoretical, and now we know that they're everywhere. But there are many of them that are undetectable because they're only visible if they're in the process of gobbling up other things. So there could be a black hole under your bed tonight. No, just kidding. Just kidding. But the nearest one is 7,000 light years away. Nothing that we're afraid of. But if you had something like the sun stray too close to a black hole, in case you're wondering what that would look like, this is what it would look like. The black hole hiding, distorting the light, bending the light of that passes near it, but otherwise invisible. And then here comes the sun. Oh no! Gobble, 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 yum, 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 gulp, 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 burp. So, yes, in a few seconds I could explain to you why some black holes are easy to see, because they've just recently had a big meal. And then the ones that are impossible to see because they haven't eaten anything in a while. So, there you go. And I've managed to, it's only 5 minutes after past time. Oh, well, I'm not going to play all this, but I'll wrap it up in a whimsical way, just in case you're worried, or maybe you're planning your next vacation and you're thinking, black holes sound interesting.
So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kinda bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't all that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly, so the chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure in your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.
Okay, enough of that silliness. So yes, I'll wrap it up now, and I hope I have time to ask questions. I know we've run out of time, but if you're willing to stick around, I'm going to answer as many questions as I can. But yeah, I'm not even talking about quantum physics, but all of this is related. You are all made out of stardust. Those explosions that make black holes also make calcium and copper. So your bones are stardust from supernovas. This whole planet is made of the remains of that. So this is not an abstract subject. The more we learn about those distant things happening in the past and trillions of miles away, the more we understand how we got here where we are now. So I hope that this encourages you to continue learning about astronomy. And I'll put up a picture to before I start taking questions so they can turn the lights up in a second. But let me show you that we have one of the biggest space radio telescopes on Earth is in South Africa now. They're leading the charge on radio astronomy in South Africa. And the Meerkat Galactic Center Mosaic, this is the black hole that's in our galaxy. the core of our Milky Way is held together by the gravity of one single black hole that has a name, Sag A star, because it's in the constellation Sagittarius, which we can see during the summertime on the southern horizon. It looks like a teapot next to the scorpion's tail. So when you're looking at Sagittarius on a summer night facing south, you're looking towards the center of our galaxy, and that's where the Eye of Sauron lives. That's actually the center of our galaxy as seen by radio telescopes. And here's a zoomed in version of Sag A star. It's 4 million times the mass of our sun. And you're not seeing the black hole, you're seeing the stuff that it is about to eat, swirling in. So, now is probably a good time to turn up the lights and see if I have some time to let you folks ask questions. Thank you very much. So now that we can see each other better, let's see who wants to ask.
And I have a microphone here. We have a couple microphones.
I'm trying to cover 13 billion years of history in an hour, so please forgive me if I ran out of time.
I got something simple.
Sure.
Matter, is it infinite? Is there no more or no less?
That is a great question. We thought that all the matter was created during the Big Bang, but now with quantum studies, there's this thing that happens, quantum fluctuations on a microscale, where a particle of matter and antimatter can spontaneously appear in an empty vacuum. We've seen it happen in the laboratory, and it must happen in space, and it's actually related to something called Hawking radiation, named after the famous Stephen Hawking. He said that if that happens, and some of the antimatter gets sucked up by a black hole, and the matter goes the other way, then the black hole is absorbing stuff that's actually dissolving it, and so he predicted that black holes could evaporate based on this.
So are black holes converting mass into energy?
Well, yes, but so does a star. A star is doing that. Every time two hydrogen atoms are fused into a helium atom, a small percentage is turned into light. So E equals mc squared. That's why, Einstein didn't invent the atomic bomb, but he realized that a small amount of matter can yield an enormous amount of energy. And that equation is what governs that, but also why the sun is losing weight, because it's giving off light. So it's literally getting lighter as it gives off light, because it's converting mass into energy. So black holes do it, but so does the sun. Oh yeah, any other questions?
Yeah, we were talking about the Webb telescope a million miles away, and the temperature around there minus 400. Wouldn't infrared light lose some of its oomph going a million miles, so it wouldn't really heat it up to room temperature?
Light gets diffused, but it doesn't lose its oomph over time, especially in the vacuum of space. If you're thinking about the heat of your wood stove, it's got to go through all this air, so it's heating up the air and it's losing oomph. But if you're in space and there's a vacuum, then infrared light is unimpeded, and so a million miles later, it's still just as bright or hot as it would have been closer. So that's a good thought, but that's when you're thinking about in a room filled with air versus the vacuum of space. It's a great question. Yes. Any others? Back there? Oh.
Hi. Just on that last question, I was under the impression that when light's going through space, there are fine particles that is impacting and it's actually weakening light. Is that incorrect?
Well, there isn't a pure vacuum. There's always, I remember learning this when I was a kid, in a cubic meter of vacuum of space, there might be 1, 2, or 3 hydrogen atoms. So imagine if the light happens to hit one of those, then it might get deflected or absorbed or somewhat diminished. But the chances of it hitting anything is very low.
Over a billion years?
Well, yeah, I mean, when light travels, it's not one photon. It'll be, quadrillions of photons. So one over here might get bounced, one over here might get bounced, but the bulk of them will stay together, coherent, like runners, in synchrony with each other. So in space, it happens, but it's just a lot less often than it would in a room like this, where there's a billion molecules floating around in a cubic meter. But trillions of molecules, really, yes.
So,
there was someone in the back there, too.
a couple of the images you had were from a radio telescope in South Africa.
Yeah.
Why is it there?
South Africa I've met some of the members of the Department of Science and Technology in the South African government, and they saw what happened to the United States with the Apollo era. For every dollar that we spent on NASA missions, we got $14 back in economic development. So all the countries of the world that want to, get to a high level of development, say a space program isn't some nice optional luxury. They consider a space program to be essential to the development of a modern nation. And so South Africa is investing a lot in its space technology and radio telescopes. They have a lot of good, land, and they're actually buying lots of land in other countries nearby to expand the size of a radio telescope. Because a regular telescope all needs to be in one package. But a radio telescope, as you saw with the Event Horizon, it can be spread out. So if you have dishes all over the world, you have a telescope the size of Earth. And so South Africa is using the African continent to build its platform. And the Meerkat is just the beginning of that. Yes, back there.
Do you have any information on the 3i Atlas?
I knew somebody was going to ask me about that. So, just real quick, 3i Atlas is the third, that's what the 3 stands for. The I stands for interstellar. So it's the third interstellar object that we've ever observed in human history. And I have a website here from the astronomer Avi Loeb, who's kind of made a splash. He used to be the chair of the astrophysics department at Harvard. He's got 3 books that he's selling about this, so he might have an ulterior motive. But basically, here's the solar system: the Sun, Mercury, Venus, Earth, the orbits you've seen before. An interstellar object means that it couldn't have started here, and it's not going to stay here because it's moving too fast. So 3i Atlas is the third time we've observed this. You may remember that we had Oumuamua, which is a Hawaiian word that means scout. I have a picture of that one here. Hold on a second. Because that was the first one that we discovered, and that was in 2017. And what's weird is we know that these objects are oblong, sound like a surfboard. Very long, very narrow. Avi Loeb is trying to help people think that maybe this is technology and not some random rock. Maybe it's like our Voyager probe, something that somebody else launched into space to study us. Now, I don't have enough evidence to prove that, but the one that 3i Atlas has an enormous amount of nickel on its surface. And on Earth, when we have a lot of nickel mixed with iron, we call that, steel. It's usually the product of industry. So it's kind of a little weird. It's also just to reemerge from out behind the sun. It's moving faster than anything we could ever send in space with rockets. And it's on a hyperbolic trajectory. So this is the telescope that discovered it, and they named it Oumuamua because everything now is named after the indigenous culture from the place where the observations were made. So Oumuamua Hawaiian because the telescope was in Hawaii on Mount Haleakala. But there's the trajectory of the first one. And it appeared in July 2017, July 29th, and look at how in a month it traveled past the orbit of... It takes our rockets about 9 months to cross that distance that it crossed in a couple weeks. And then the gravity of the sun bent its path, but when it got around here, it accelerated greater than can be accounted for by gravity. It could be because there was ice on it that evaporated and acted like a little jet that boosted it, gave it a little extra speed. Or it could be aliens. Obviously I'm kind of mocking that because that's probably the least likely possibility. But the new one is also doing something similar. It's actually getting accelerated by something more than just gravity alone. The 3i Atlas that you asked about is like Oumuamua, but even faster, and it's changing color, and it's got complex things like nickel on its surface. Still not proof that it's made by aliens. But it's probably a good idea to keep a lookout on it, just in case. Well, yeah, so like I had this picture up earlier, we did the same thing, right? If it is aliens, it would make sense because we sent probes out into space that are never going to return on trajectories that will never go back to the sun. We call that hyperbolic, like hyperbole. It's going so fast that the gravity of the sun won't be able to rein it back in. It's just going to keep going. And we just had one a few years ago, and then we had a second one called 2i Borisov, and now we have 3i Atlas named after the telescope that saw it. And, so Avi Loeb is like, is this like the sequence? Like they send a little one, and then they send a bigger one, and then they send the mothership. We've watched all too many sci-fi movies, but it is a fascinating thing, but it's also, we have just come to that point where we have telescopes sensitive enough to see these things. So this might be happening all the time, and we might be freaking out like Chicken Little thinking the sky is falling just because we discovered it recently. That might be all there is to it. But it could be, remember supernovas? If there was a rock flying around a supernova and it got hit by that blast wave, it would be going that speed, and it could be a shard from a world that was shattered by a supernova, and that could be all that it is. That would explain it, but it's not as exciting. It won't help sell as many books. Yes.
So do you just keep watching it forever?
I'm checking the news every day. I mean, everybody with a telescope is pointing at 3i Atlas because by around Christmas time, it's going to be close enough that you might be able to see it with binoculars from your backyard. It won't look like much. It's not like you're going to see it with flames shooting out, like a race car. It'll look like a dot in the sky, but it is moving very fast. And if you took pictures every day, you would see it streaking its path through our solar system. So I don't know what it is, but it is certainly exciting to follow that. Thank you, Marita, and I should say thank you to Bright, who's actually doing the recording, because Bright's name reminded me of a perfect limerick to send us on our way. You've probably heard it before. He's a young man, but this one is about a young lady named Bright, whose speed was far faster than light. She set out one day in a relative way and returned on the previous night. So, and that's why you can't go faster than light, because you literally break time. Maybe somebody's figured that out, but so far not here. So, thank you all for coming, and I'll stick around and answer questions as you filter out.